So, hello everyone. Good to see you all. So, yeah, good to see everyone.
Hello.
Hello. Oh, hi, Henry.
Hi. Hi. Nice to meet you, Lewis.
Yeah, good to meet you. So I'm just busy. We can, probably it would be good to wait just a few minutes just while everyone is arriving.
Sure. Should I try to test my screen share?
Yeah, that'd be great.
Okay, just give me a second. So do you see the slides?
Yes.
Okay, great.
Yeah, they look.
Okay, so that should be pretty straightforward.
Oh, okay. So I am recording. Just checking. Okay. So great. So you know, we're very happy to have Henry Yuen from the University of Toronto talk about an overview of MIP star equals RE and some of its ingredients. So maybe I should just say a few words. There's a chat button that you can use to write questions down. And you can also, there's a hand raising button. If you press participants, then you see a list of participants and there's a button for raising your hand. So if you raise your hand, then I can pause and or if you write a question, then I can relay the question to Henry. Okay, so with that, I guess there's, right, so I guess there's nothing, I guess we can get started.
Great.
So yeah. Please go ahead, Henry, yeah.
Okay, great. So hello, everyone. Yeah, thanks for the introduction, Lewis. And also thanks for the invitation to speak on this online seminar. So I'm going to give an overview of the MIP star equals RE result. And this is joint work with Jiangfeng Ji, Anand Natarajan, Toma Vidic, and John Wright. I'm going to describe some of the components of the proof. And I won't assume any particular background in computer science or quantum information theory. But if anything is unclear, please feel free to stop me and ask, or you can type it in the chat, and hopefully maybe Lewis can bring it to my attention. All right. So this talk is broken down into several parts. First, I'm going to give a brief overview of Tsirelson's problem which is about comparing different quantum correlation sets and how it connects to Kahn's embedding conjecture. If you attended Lewis's talk a couple weeks ago, this should be a refresher of the last part of the talk that he gave. Then I'm going to talk about how Tsirelson's problem connects to a question about the computability of something called non-local games. And this will explain how answering a computability question has consequences for Tsirelson's problem and therefore Kahn's embedding problem. And then with that in mind, I'll highlight two important components of the MIP star equals RE proof. One being a recursive compression technique for games, and that in turn relies on having very efficient tests for high dimensional entanglement. So that's the outline, and let's get started with correlation sets and Tsirelson's problem. So Tsirelson's problem is about quantum correlations, but first I should explain what's a correlation. It's some mathematical model for the behavior of a physics experiment involving two separated systems. Let's call them box A and box B. And each box takes in an input. And for example, box A takes some input X. And these inputs come from some alphabet of size n. And each box produces an output, one of K symbols. And we can think of the input as telling each box to perform some specific measurement of whatever is inside this box. And the output is the outcome of this measurement. And we can describe the joint input and output behavior of these two boxes using some conditional probability distribution, P of AB given XY, the probability of these two outputs given their inputs. These correlations can be represented as vectors in real space, these four tuples of inputs and outputs. And in this talk, we should think of these boxes as being very separated very far from each other, so they cannot communicate or send signals. And the question that people are interested in is, well, what types of correlations are physically reasonable? And it depends on your model of physics. So, if your model of physics is classical, then you get something called a set of classical correlations. These are built out of deterministic correlations where the outputs of each box are just a deterministic function of their inputs. And you can also take convex combinations of these deterministic correlations. And that comprises the set of classical correlations. So we can give this set a name. So if you fix the number of, the number of allowed inputs and outputs, n and k, we write C sub c, n comma k to denote the set, denote the set of classical correlations. So it's some convex set in real space. But we believe that nature is not described by classical physics, but rather by quantum physics. And so here, the set of correlations appear to get richer. And the reason they become richer is, at least from a physical level, it comes from something called quantum entanglement. And the way we mathematically model this is we say that a correlation is quantum spatial if it's given by this inner product formula that's shown in the first line. And basically, for each box, we associate a Hilbert space, one for each box. These Hilbert spaces can be infinite dimensional. And there is some unit vector psi that lives in the tensor product of these two Hilbert spaces. And this unit vector psi describes the joint state of these two boxes. And when each box gets an input, for example, when box A gets input X, it performs a measurement on its particular internal state. And measurements are described via something called POVMs, which are sets of, for every possible input X, there's a set of positive operators indexed by outputs that sum to identity. And there's a, for every input, there's a set of, there's a POVM. And the rule for, the probability of getting a particular pair of outcomes is given by this inner product formula that you see above. And the important thing to note here is that the probability depends on the tensor product of the two measurement operators between box A and box B, right? And this tensor product assumption is a natural way to model spatial separation. Okay? And so this is a model that's very commonly used in quantum information. And we can give this, this set of quantum correlations a name. We call it C sub QS, the set of quantum spatial correlations. And if we restrict the Hilbert spaces to being finite dimensional, then we get the set C sub Q. Okay, these are the set of finite dimensional correlations. And there's another set that we'll consider, which is the closure of the finite dimensional correlations. So we call that CQA. Okay, so, or the approximately finite dimensional correlations. So there's a more general way of modeling quantum correlations called the commuting operator model. And here, there's only one Hilbert space to describe the joint state of these two devices. And the state of the two devices is, again, described by some unit vector, but there's no tensor product decomposition a priori. And each device has their own set of POVMs that describe the measurements that they can make. These measurements act on the same Hilbert space. The only constraint is that the measurements of box A must commute with the measurements of box B. So this is a more general model of quantum correlations. It contains all of the quantum correlations that you saw before that were in this tensor product model, but could possibly contain more. And we let the CQC denote the set of quantum commuting correlations. Okay, so we have described a bunch of different correlation sets, and they form these chains, this chain of inclusions. Okay, something that people have wondered for a while is which inclusions are strict. So on the very left, we have the classical correlations, and they're contained in the finite dimensional quantum correlations. It was proved, back in the 60s by John Bell that the set of quantum correlations is strictly bigger than the set of classical correlations. Okay. And it took a few years later, for Slostra to realize, the second separation, and he showed that the set of spatial correlations, CQS, is not closed. So, just as a reminder, spatial correlations are correlations in this tensor product framework where the Hilbert spaces can be infinite dimensional, but it's not closed, so it's not contained in this closure CQA. And then, the year after Coladangelo and Stark showed that, there's a separation between the finite dimensional and the infinite dimensional correlations in the tensor product model. And that leaves the final inclusion, which is whether CQA is equal or not to CQC. And this is Tsirelson's problem. The way to interpret this is whether, it asks whether all commuting operator correlations can be approximated by finite dimensional correlations. So this question, people realized about 10 years ago that this question connects to some deep questions in mathematics. And so this CQA equals to CQC, whether that's true, turns out this is implied by Kirchberg's QWEP conjecture. And this was proved simultaneously by Tobias Fritz and also Yuen, Vasquez, Palazuelos, Perez Garcia, Schultz, and Berner about 10 years ago. Turns out that this Tsirelson's problem was actually equivalent to Kirchberg's conjecture. The converse was shown by Ozawa. And the thing we know about Kirchberg's conjecture is that it's actually equivalent to the Kahn embedding conjecture. Okay. So all three of these questions, Tsirelson, Kirchberg, and Kahn, these questions are all equivalent. A yes answer to any one of them implies a yes answer to all of them. Okay, so before I go on, any questions about quantum correlations and Tsirelson's problem?
I guess not.
Sure. So let me continue on to non-local games. So non-local games are a way of having an operational interpretation of these correlations, and gives a way to think about what you can do with them and compare their different abilities. So what's a non-local game? Well, it's a game that you play with these two boxes. And a two-player non-local game has two pieces of information. One is a probability distribution over the two inputs that the boxes might receive. So we call that mu. It's a question distribution. And it also comes with this function d, which maps inputs and outputs to these devices to 0, 1. Okay, and this is called the decision predicate. And the way we think of this as a game is, there's some verifier that first samples a pair of questions x and y from this distribution mu, sends the questions to the boxes produce their answers, and then based on the questions and answers, the verifier will decide whether the boxes win this game. Okay. And we'll call the boxes players from now on, because they're playing a game. Okay, so that's a non-local game. And the behavior of the players can be described by correlations between them. So given a game, how well they can succeed in a non-local game depends on what types of correlations you allow the boxes to use. So if the players use some fixed correlation P of AB given XY, then the success probability of that correlation in a game G is given by this formula, omega of GP. So it basically says you look at the probability of sampling a pair of questions XY, and the probability that they produce some pair of outputs A and B, given this correlation, and then you only sum over the answers which win the game, according to this decision predicate. So notice that this is a linear functional on the correlation. And the linear functional depends on the description of the game. And as I said, depending on what types of correlations you allow the players to use, they have different optimal success probabilities. So for example, if you allow the players to only use classical correlations, then you get what's called the classical value. This is denoted omega C, and this is the supremum of the success probability over the classical correlation set. And similarly, if you allow the players to use quantum correlations, in particular the finite dimensional correlations, then we get something called the tensor product value. So this is omega Q of a game G, take the supremum over the set C sub Q. And notice that since we're taking a supremum, this is the same as optimizing over these other sets, CQS, and CQA. CQA is this closure of CQ. So that's the tensor product value. And finally, we have the commuting operator value, which you take the supremum over the biggest set we've talked so far, CQC. Okay, so we have these three different types of values associated with a non-local game. And a natural question is, are there games for which these values differ? So let me describe, maybe the most famous non-local game called the CHSH game. And this is a game that comes from physics in the 60s. And it's essentially, it was discovered shortly after Bell discovered his theorem. And so the rules of the game are quite simple. So the questions and answers are all bits. The question distribution is just the uniform distribution. And the players win if and only if the parity of their answers, A plus B, is equal to the product of their questions, X times Y, modulo 2. So it's a very simple game, but it exhibits a separation between the classical and quantum values. So classically, the players can only succeed with probability 3/4. But quantumly, they can do better. They can, whether they use finite dimensional strategies or, these commuting operator correlations, the maximum success probability they can achieve is this 0.854 value. And, the significance of this is that this number has been experimentally tested. They actually play this game in experiments, and they do witness a winning probability that's greater than the classical value. So that's the physical significance. Okay, so that's an example of a non-local game. And now let me turn to this question of computability, right? So back in 2004, there was some computer scientists thinking about complexity theory and its interaction with quantum information. And they asked, we have this quantum value, this omega q. Is there an algorithm to approximate this number? So what we really mean is, we would like some general procedure. Let me see if I can move my mouse. Where the input to this procedure is a description of a non-local game G, which is the rules of the game and the question distribution, and some precision parameter. And you would like the algorithm to output some additive approximation to the value, the tensor product value, omega q, of this game. And if there is an algorithm, then natural follow-up questions would be, if there's an algorithm, what is the fastest one? If you could approximate this omega q, what other problems could you solve? Can you reduce, can this problem of approximating omega q be reduced to solving some other problem, right? So these are natural computational questions that immediately come to mind when you think about this. And let me just quickly say, why is this a naturally motivated thing to ask? Well, it comes from classical theoretical computer science. So Steve Cook in the 70s, came up with the theory of NP completeness. And one way of, phrasing what he proved is he showed that computing the classical value of a non-local game exactly is an NP complete problem, right? So these games are not simple objects, right? To do this, even in the, to optimize over the set of classical correlations is challenging for algorithms. And he studied the case of computing this value exactly. About 20 years later, people asked, well, what about approximating this, this classical value up to some additive error? And people showed that it's still NP complete. So you pick your favorite epsilon. It could be, say 1% or something, or a half, or any number less than 1. Giving an additive approximation to these non-local games is still an incredibly difficult problem. It's an NP complete problem. And this result is known as the probabilistically checkable proofs, or PCP theorem. And you might have heard of the PCP theorem also being formulated as the following. It says that proofs of mathematical statements can be encoded in a robust format in a way that if you wanted to check the correctness of a proof, you only need to examine 3 bits of the proof at random, independent of how long the proof is. And with a high degree of confidence, you can verify whether the proof was correct or not. And this is equivalent to this NP completeness statement. Okay, so that's the motivation for from the classical side. And going back to whether there's an algorithm for approximating omega q. And there's some immediate barriers to even coming up with a trivial algorithm. So in the classical case, there's a very simple algorithm to compute the classical value. You simply enumerate over all possible deterministic strategies for players. And since the classical correlation set is the convex whole of these deterministic strategies, this does allow you to optimize over, find the optimum value success probability in exponential time. Okay. So this is something you can do. But it's not clear if there's a similar trivial brute force algorithm for the quantum value. Okay. And in fact, if you wanted to compute it exactly, there is no algorithm. And this is something that William Slofter showed in 2017. And this was a consequence of his work in showing that the set of spatial correlations is not closed. So already we see some differences between the set of quantum correlations and the set of classical correlations. In the exact case, these quantum correlations are impossible to optimize over. But then you can ask about, what about if you just wanted some approximation? And still we don't have, we don't know of any, can't think of any algorithm to do so. And the major barrier comes from the fact that there's no generic upper bound on the dimension of, correlation that you would need to play optimally in any given non-local game, right? So you can imagine that you could try to do some sort of search over the space of these finite dimensional quantum correlations, but given a game, you wouldn't know what's a good dimension to look for. You can start with, say, dimension 2 strategies, it's dimension 3, dimension 4, and so on, but you wouldn't know where to stop. Okay. So it's quite unclear, whether there's an algorithm. So now this connects to the problems I described earlier, Tsirelson's problem and the Kahn embedding problem. And it turns out that if the first two problems have a positive answer, then it actually implies the existence of an algorithm to solve this approximation problem. Okay, so that's the connection. So, and this algorithm, if the Kahn embedding conjecture were true, then Tsirelson's problem would be true. Then this supposed algorithm has two procedures, one called search from below and one called search from above. And so I'll describe those two next. So the simplest one to start with is the search from below. And this is kind of the attempt at coming up with a brute force algorithm. So the search from below procedure computes an infinite sequence of real numbers, alpha 1 and alpha 2, alpha 3, that are non-decreasing. And all of these alpha numbers are lower bounds on the tensor product value of your non-local game G. And what is each alpha D? For a fixed D, alpha D is some epsilon approximation to the best D-dimensional strategy for G. And if you fix a D, you can compute this number. One way to do that is just by searching over an epsilon net on the space of D-dimensional correlations, which is a compact set. So you can do this in finite time. And by definition, as you increase the dimension that you consider, for a large enough dimension, your sequence alpha D will approach the tensor product value of G. Okay? The issue is you just don't know how fast it's converging. So that's why this search from below by itself doesn't give an algorithm. But we can combine it with the search from above procedure, which computes a sequence of upper bounds, these beta 1, beta 2, beta 3, on the commuting operator value of G. Okay. And each beta D is the best upper bound on this commuting operator value of a game that can be certified by a sum of squares of degree D non-commutative polynomials. Okay. So that's somewhat abstract, but the important thing is that for a fixed D, again, beta D is computable. And it's computable by something called semi-definite programming. And there's something called the NPA hierarchy that allows you to compute this number beta D. And we also know that as you increase D, the degree of the polynomials that you consider, this sequence of upper bounds converges to the commuting operator value of a game. All right, so now we put the two together, and if you assume that Tsirelson's problem has a positive answer, meaning that the set of commuting operator correlations coincides with the CQA, the approximately finite dimensional correlations, the lower bound sequence and the upper bound sequence must converge, right? So you basically run both procedures in parallel, and you just wait until the two numbers, alpha d and beta d, come within epsilon, in which case you know you've homed in on the tensor product value, which is the same as a commuting operator value, assuming that Tsirelson's conjecture is true. Okay. So this does not give an efficient algorithm, but it's guaranteed to converge under this assumption of Tsirelson. So, so maybe I'll pause here. So are there any questions about this algorithm and why its convergence is implied by the Tsirelson's problem? Okay.
So I don't have any questions. I'm just waiting to see if anybody's written anything. But yeah, so far so good.
Great. So that's, if we could prove, Tsirelson's, or if we could prove the con-embedding conjecture, then this would imply Tsirelson, and therefore it would imply that there's at least some algorithm for approximating the tensor product value. So this brings us to the statement of our result, MIP star equals RE. There's a couple ways of formulating it. I'll say it this way. So it implies that there exists a computable map from Turing machines to non-local games with the following property. So you walk up with the Turing machine M, you can transform it into a description of a non-local game G sub n, where if the Turing machine halts, meaning that you turn on the Turing machine and you just run it until it decides to terminate. If it does eventually terminate, then the tensor product value of this game is 1. Whereas if the Turing machine never terminates, if it never halts, then the tensor product value of this corresponding game is at most 1/2. And this constant 1/2 can be replaced by any constant less than 1. It's not so important what it is. Okay. So the implication of this, well, we know, from, Alan Turing, and he proved that there is no algorithm that can solve the halting problem, right? No algorithm can decide whether a general Turing machine will halt or not. So in particular, it means that there's no algorithm to approximate the tensor product value of non-local games up to any precision epsilon. So in particular, this search above and search below algorithm that I described a few slides ago cannot converge for all possible non-local games G. So therefore, there must exist a game G for which the tensor product value and its commuting operator value must differ. And that means that Tsirelson's problem has a negative answer, and therefore the con-embedding conjecture is false. So that's the sequence of implications. So let me say a little more about whether there exists an explicit counterexample, right? So this argument says that there exists a game G, but can we actually pinpoint a game, an explicit game G that has a separation? And furthermore, can we, something that probably people are more interested in is, can we pinpoint a concrete counterexample to the con-embedding conjecture? So, so we know that there must be some Turing machine M for which the tensor product value and the commuting operator value of the corresponding game must differ. Which Turing machines M have this property? Well, it should be, and we don't know this, so this is an open question. It should be that for any Turing machine M that does not halt, the two values must differ. And what we believe is, for example, if you take the Turing machine that just trivially gets stuck in an infinite loop, the commuting operator value of this game should be 1. We know that the tensor product value of the game is at most a half. That's what we proved. But we don't know how to reason about its commuting operator value. Okay. But we think for any non-halting M you walk up with, this should be the case. We can, by using a similar construction, we can point to a specific game G that does have this separation. So that's something we can prove. This explicit separating game G is a synchronous game. So I won't describe what a synchronous game is, but Lewis talked about it last time. And by known results by Paulson, Severini, Stalke, Todorov, and Winter, if you were able to, for this specific game, if you were able to exhibit an explicit commuting operator correlation, you were able to provide some description of it that achieves this winning probability of 1, this would directly yield an algebra without the con embedding property. And another, some people have asked me, well, this explicit game that we come up with, how big is it? How many questions and how many answers? Well, it's probably less than 10 to the 20. We didn't try super hard to do an accounting. And the reason is it's because the description of the game is rather complicated. It involves a Turing machine that executes this NPA semi-definite programming hierarchy that I described earlier. And that, I've never programmed the NPA semi-definite programming thing. But I imagine it requires some fair amount of code, and to translate into a Turing machine, there's probably some overhead there. The point is, there is some finite, it is some constant size object that we can describe, but it's kind of hard to, to get a very good grasp on what the game looks like. Okay, so.
Okay, so I could stop you. We have a question from the audience. What would be the number from Michael de la Salle? What would be the number of questions and answers for the trivial Turing machine that you alluded to on the previous slide?
Oh, good question. It probably much smaller. I don't think it would get to the something as small as, like, say, 5 questions or 3 answers, like these other separating non-local games that people have come up with. That's because, in our construction, we have this very large, there are many steps to it, and, there are lots of constants involved that probably add up over time. So it's probably not going to be a very nice number. If you were to, force me to come up with some estimate, I would say it'd probably be in, like, the thousands. But, that's just a complete guess on my part. It's not nice enough that we can say, oh, it has like 20 questions or something like that.
Oh, okay. Yeah, okay, thanks for
Okay, so let's see. Any other questions? All right, so let me continue. So that was an overview of our results. We saw how it connected, this computability question to the Tsirelson's problem. Then let me describe, how some ingredients for how this result is proved. The first ingredient is something called recursive compression of non-local games. So to describe this, I have to sort of say a little more carefully, like, how do we actually represent non-local games? Like, how do we have a description of them? And it'll be useful to describe them in the language of Turing machines. So recall that in a non-local game, it has these 2 parts to it. The verifier will sample questions from some distribution, and it will compute some function D, this decision predicate. So we'll assume that a non-local game is represented by some Turing machine that specifies the behavior of this verifier. So, just think of it as some computer program, maybe written in your favorite high-level language, that just implicitly describes how do you sample from this question distribution and how do you compute this decision predicate. And there's a lot of flexibility in how you have this representation, but the important thing is just represented by some computer program.
Oh, but by the way, so we have a question from Josh Frisch. Is the number of questions and answers required to be super polynomial in the length of the Turing machine code?
Good question. The description, okay. So it's going to be, so the description of the non-local game will be polynomial in the size of the Turing machine description. And at the number of questions and answers will be at most exponential in the description size of the Turing machine. So it is super polynomial, but yeah, it's at most exponential.
Okay, yeah, that's yeah, great.
So, but actually that's a good question because it ties into the next thing I wanted to say, which is that a very important measure for us will be a complexity measure of a non-local game, which normally people measure the complexity of a non-local game by the number of questions and answers. Here we'll measure it by an upper bound on the time complexity of the verifier of G. So I said that we'll describe verifiers by some computer program, and computer programs have some time complexity. And so I'm going to associate the complexity of a game with the time complexity of the verifier. So going back to the previous question, what is true is that the complexity of G sub m is only polynomial in the description of M.
So if I could just stop you for a moment. So just to confirm, you're given a Turing machine, and then from this Turing machine, so there is a Turing machine which accepts as input a Turing machine, and then as output, it computes a non-local game, or?
Yes.
Okay.
Well, so it takes in a description of a Turing machine M and outputs another Turing machine that describes a non-local game.
Okay, that's what I was, okay, I understand now.
Okay, yeah, that's a good question.
So it accepts as input a Turing machine, the output is another Turing machine, the output is polynomial in the input, and the output Turing machine computes a non-local game.
That's right.
And the non-local game, though, can have exponentially many, exponential number of questions and answers in the size of the original Turing machine.
Exactly.
So here's a question from Michael De La Salle. Could you repeat what running time of the verifier means? Good.
So one way to think about it is, so this decision predicate D of x, y, a, b, you can measure how long it takes to compute its output 0 or 1 as a function of the length of x, y, a, and b. So, so in this non-local game, this complexity of this non-local game is, like, for example, how long it takes to compute this decision predicate. And also you can think about when sampling from this question distribution mu, there's also some number of steps that the computer program will take to do that. And you also count it towards this complexity.
Okay, yeah, great.
Okay, hope that made sense. Okay, so basically we view everything as a Turing machine, and this is helpful because we can sort of interconvert between non-local games and Turing machines and so on. And let me introduce just a couple more bits of notation. So I actually want to talk about an infinite family of non-local games, right? G1, G2, G3, so on, but I want them to be uniformly generated, meaning that for this infinite family GI, there's a single Turing machine that I'll call G hat that implicitly describes all of them. So this G hat will take in some integer n, and it outputs the non-local game G sub n, right? So technically it outputs a Turing machine. It's a Turing machine that outputs a Turing machine, but this output Turing machine describes a non-local game. All right, so, and it's important to note that this G hat is just some fixed object that specifies an infinite family. Okay, so that's one piece of notation. The second piece is something I'll call the entanglement lower bound. And this is E of G comma P. So G is a fixed non-local game. P is some probability. And this is the minimum dimension entanglement. We're only thinking about finite dimensional correlations now. The minimum dimension entanglement needed to achieve some success probability P in this game. So as an example, let's think about the CHSH game. To achieve probability 3/4 requires zero-dimensional entanglement because you could achieve it with a classical strategy. To achieve this 0.854 value, you need two-dimensional entanglement. To achieve value 1, well, there is no finite dimensional strategy that achieves this. So we say that this entanglement lower bound is infinite. Okay, so now this takes me to the main technical result, which is the compression theorem. And this, there's a bunch of pieces here, so I'll go through this slowly. So it says that there's some computable map compress. Okay, so this is some, think of it as some computer program where if you provided it some G hat, okay, so G hat is something that specifies an infinite family of games where each of these games in this infinite family has polynomial complexity in n. So for every index n, the complexity of G sub n is poly n, and this G hat specifies all of those games simultaneously. Okay. So you're going to take this infinite family of games and plug it into this compress via this G hat, and it's going to output another infinite family of games F sub n through this Turing machine F hat. Okay. So it maps families of games to family of games where, what do we know about the output family? Well, the complexity of each of these Fs is not polynomial n, but actually polylogarithmic in n. So it's much smaller. So there's some complexity reduction. And the relation between the G's and F's is we have this completeness preserving property where if the value of G sub n is 1, then so is F sub n. And we have a relationship between the amount of entanglement required to play F sub n with the amount of entanglement required to play G sub n. So there's actually two lower bounds here. So in order to win F sub n with probability at least a half, you need at least either 2 to the n dimensional entanglement, or the amount of entanglement needed to play G sub n, whichever is greater. Okay. So this slide is very important. So maybe it could take like 10 seconds to stare at it and let it sink in.
So I have a question.
Sure.
Right. So if one only, so my understanding or my guess is that the main result MIP star equals RE is stronger than Kahn's embedding conjecture, and that one could, if one just wanted to prove Kahn's embedding conjecture, then you don't need to know about the complexity of Fn here. Because you only need to know that in the end, you only need to know that there is some separation. So I guess I'm not quite saying this correctly, but I guess what I'm trying to say is that you're getting a bound on the complexity of the verifier. And if you weren't concerned with the complexity of the verifier, then maybe you wouldn't, you wouldn't be able to prove MIP star equals RE, but you could still show that Kahn's embedding conjecture is false. You could still get the separation in Tsirelson. You could still resolve Tsirelson's problem.
Right. So at least for the way we're proving it, the most important thing, it's not so important that it's polylog. I mean, that's a pretty dramatic reduction in complexity. It just cannot increase beyond, like this this, whatever the complexity of Fn it should be less than the complexity of G sub n. So any non-trivial savings that you have in the complexity would allow you to prove it the way we've done. Yeah, but I mean, if the complexity is allowed to, I mean, let me put it this way, like if you didn't insist that the complexity of F sub n shrinks, then this theorem is actually kind of trivial in the sense that you can just say F sub n is actually the same as G sub n, you're just relabeling. I mean, okay, you have this dimension lower bound, this 2 to the n, but that's, you can sort of just shoehorn that in, but you wouldn't be able to prove something non-trivial. So, at least for this particular theorem, it's very, very important that there is some complexity reduction.
Okay, thank you.
Mm-hmm. Okay, so given this compression theorem, like, how do we get this reduction from Turing machines to non-local games? And we're going to apply this compression theorem recursively. So let's fix a Turing machine M. Okay, this is the one that you want to decide whether it halts or not. And we can come up with a family of games that depends on this Turing machine. So I'm going to define this family G sub n. So for every n, there's a different game. And here's the description of the verifier for each of the G sub n's. So the verifier, the first thing it's going to do, it's going to take this Turing machine and run it for n time steps. And if this Turing machine halts within that time, the verifier is just going to accept. So the verifier doesn't actually even interact with the two players. It just automatically lets them win. If the Turing machine has not halted in this time, it will proceed to do something else. The verifier will compute, it will run this compression procedure on G hat. So G hat so this is a self-referential step. G hat describes an infinite family of games, including itself, right? So itself being G sub n. But this is something that you can do. You can have these self-referential calls in computability theory. And it outputs this new family of games F hat, and it's going to play the non-local game F sub n plus 1. Okay. And it's just going to play whatever rules F sub n plus 1 specifies. So this is the game. And so the first question we should ask is, well, what is the complexity of this game G sub n? And we need to define it properly so that the complexity is poly of n. And this is because we need this compression theorem to be applicable, right? This is a condition needed by the compression theorem. And so that we can say something about what F hat does. Okay, so, and the intuition for why it's poly n, well, the first step takes n steps, right? Because you're running this Turing machine. The second step essentially takes a constant amount of time because this G hat does not depend on n at all. So this is just some constant size object, and this compression procedure only takes a constant amount of time. This non-local game F sub n plus 1, it takes, you kind of have to be a little careful, but roughly speaking, remember that F sub n plus 1 should be polylogarithmic in its complexity. Of course, this was what's guaranteed by the compression theorem, which is what we're trying to apply. But you can arrange it so that it all works out. So this game really does only have polynomial complexity.
So So you're talking about the complexity of games, but I guess this is, I mean, I guess what you really mean is that you've got a Turing machine, which is representing the game, and it's the complexity of the Turing machine.
That's right.
Okay.
You can imagine that each of these steps can be sort of written out in, you know, some computer code language that tells what the Turing machine what to do in order to decide whether to accept or reject, and so on. Okay, so that's the complexity. So you know, now that we know this complexity, we know that we can actually apply the compression theorem. And now the interesting question was, what is the value of this game G sub n? So let's break it up into two steps. So step one, m halts in some time t. It's just some integer t. So immediately, just from the description of the game, we know two things. So if the index of this game n is greater than t, then we know that the value of this game is 1. And that's just because step one always accepts, right? So that's easy. What about if the index n is less than the time, you know, this halting time m? So step one never accepts, so it always continues to step 2 and 3. And then the game Gn is simply the same as the game f sub n plus 1. It accepts if and only if the game f sub n plus 1 accepts. So the two values of these games are the same. So now we want to invoke the compression theorem, right? And the compression theorem promises us something about f. And it tells us that if you look at G sub t, we know that its value is 1. So therefore, f sub t is also has value 1. But when you can propagate this down to this fact down to the value of the game G sub t minus 1, and we also know that this G sub t minus 1 also has value 1. And so you can imagine where this is going. You just repeat this argument all the way down to G sub 1, and for all n, G sub n has value 1. Okay. So this is the analysis in the case that m halts in this in some time. So all these games have tensor product value 1. Okay, so the more interesting case is, what about the case 2 in which m never halts? And this is where we use the entanglement lower bound to reason about its value. So if m never halts, then this step 1 never matters, right? M never halts, so we never accept here. So we're always playing this compressed game f sub n plus 1. So the entanglement requirements of G sub n is the same as the entanglement requirements of f sub n plus 1. And now we invoke the dimension lower bound that we know on f sub n plus 1. One of the lower bounds is that whatever you need to play f sub n plus 1 is the same as at least as much as what's required by G sub n plus 1. And you know, you can sort of just repeat this argument so that you see that for any fixed n, the entanglement required to play G sub n to win with probability at least a half, I'm dropping the halves just for clarity, it's greater than E of f sub n for any integer m. Okay. If you combine these two facts above. And now we use the second part of our dimension lower bound, which is that the entanglement required to win f sub m is at least 2 to the m, right? So this implies that the amount, you know, the dimension you need to win G sub n is at least 2 to the m for all m. So there's no finite lower bound, which means that you know, you need essentially an infinite amount of entanglement to play G sub n to win with probability a half. And that tells you that the tensor product value of G sub n is at most 1/2. So, you know, you put everything together, what is our final reduction? Well, you give me a Turing machine M, I'm going to compute the description of this game G sub 1. I'm going to set the index n equals to 1. And this gives us our final reduction. So if m halts, the value is 1. If m does not halt, the value is at most 1/2.
So we have a question from Michael De La Salle. So from the pseudocode description of G sub n, how do you obtain a game? You know, that is, how do you obtain a question distribution and a decision predicate?
Right. So, you know, I guess it depends on how, you know, I didn't specify how exactly you encode verifiers as non-local game, as a Turing machine. So the way we did it in our paper was to say, actually, there's essentially two Turing machines, one for sampling from, telling you how you sample from the question distribution. So you know, this Turing machine will take as input just some random string of a certain length that's uniformly random, and it produces a pair that's distributed according to mu. Okay, and however it does that, that's you know, just that's its function. And then the second Turing machine will compute this decision predicate d of x, y, a, b. And whenever we specify a non-local game, you just walk up with these two Turing machines. And so from the pseudocode, you know, it's written a little informally, but essentially everything here describes what the decision predicate is doing. And you know, so that, you know, the decision predicate will compute this compression function to compute the decision Turing machine of the output game, and also the Turing machine that samples from the question distribution. So it outputs a pair. And the sampling Turing machine will also do the same thing. So you just sort of separate it out into these two pieces. I hope that made some sense.
Yeah.
Yeah. Okay. So that's the recursive compression argument. I think I'm close to out of time. So I was going to say something about these efficient tests for entanglement, but you know, maybe I should stop now to let people leave if they need to, or?
Well, I'm happy to stay. So we do have a question. Could you tell us a bit more about how the complexity reduction is done, or some intuition to what it means?
Right. So how is the complexity reduction done? So there's two parts to that, and you know, the first part of it is this ingredient 2 that I'll discuss. So maybe I'll launch into that, and hopefully they'll partially answer that question. If that's okay.
Yes.
So
yeah, you know, so I'm happy to stay, and of course, if people need to leave, then people need to leave. But I think that there's enough people who want to stay that we can continue on. Okay, great. Yeah, it won't take too much longer. But yeah, let me say some bits about these efficient tests. And this is a large part of where the complexity reduction comes from. And so, you know, this is the compression theorem again. And these tests for entanglement, so really in some sense, the interesting parts of this theorem are these two things I've circled in purple. One is, you know, somehow you're certifying that at least, you know, for every one of these games, f sub n, there's an entanglement lower bound, dimension lower bound of 2 to the n. But you're doing this, you know, this is non-trivial because the complexity of this game is polylogarithmic in n. So there's a huge, you know, there's this huge gulf between how much work this f sub n verifier is performing and how much entanglement it's certifying, so to speak. So let me try to give some glimpse of, you know, and this is, you know, this big difference is really what allows us to do this compression. So to sort of explain this, I'm going to go back to the CHSH game really quickly.
So here's just a reminder of what this game is. It's this very simple rule. It has this 0.854 quantum winning probability. And one way of thinking about it, it says, if you're playing this game with these two boxes and you observe a winning probability of greater than 75%, this indicates the presence of some entanglement, right? But it can say much more than that, and it has something called a rigidity property, which is very, very useful. So let me say, what the textbook quantum, when you open up a quantum information textbook, it gives you a description of a strategy for this CHSH game that wins with the this 0.854 value. So it's some correlation, and it's a simple correlation. All the dimensions of the Hilbert spaces is just 2. So the shared state is in this tensor product of C2 tensor C2. Okay, it's something called the maximally entangled state. And here's a description of the measurement operators. So if you look at, just forget the B's for now, let's just look at the A's. So when the first box gets question 0, it performs a measurement that has these two projectors, A00 and A01. If you take the difference of the projectors, you get a unitary, A sub 0, that is this sigma Z matrix, okay, this poly Z matrix. And if you look at the corresponding unitary when the question is 1, you get something that's the sigma X matrix. The important thing about these two matrices is that they anti-commute. Okay, so, and there's a similar relation for the Bob's operators, B0 and B1. Okay, these unitaries anti-commute, and this is a description of this optimal strategy.
So these are not positive operators. At least A0 is not.
Right.
That doesn't matter, or yeah, anyway.
Oh, right. So the positive operators are the A00 and A01. Those are the projectors. Okay. And when you subtract them, you get this unitary. So it's sort of a way of encoding, it's sort of a way of packaging the projectors into one object.
Oh, okay, I understand, yes.
So yeah, they're unitary and they anti-commute. But what about general strategies? So if you walk up to me with a correlation that achieves an optimal winning probability of this 0.854, you actually can deduce something about the structure of these operators. And for example, in the CHSH game, it forces anti-commutation relations between A0, A1, and A1. Okay, so A0 times A1 applied to the state is equal to minus A1, A0. And the same for the B operators. And this is something that you just deduce generically from the fact that they have this optimal winning probability. And furthermore, once you know this, there exists local isometries. The isometries are local to each box's Hilbert space, under which they're called observables, A0 and A1. If you apply the isometry, they look like the sigma Z and sigma X operators, which is this textbook strategy that I described. And also under these isometries, the state looks like this maximally entangled state on this 0, 0 plus 1, 1. Of course, if the state psi that you walked up with was much, was an arbitrary dimension state, it was dimension like 1,000, this isometry would extract out these two dimension, a two tensor product of C2 tensor C2 and identify this state inside. And these operators A0 and A1 would only act on that part of the space. So this is what we mean by rigidity. You play this CHSH game and you take any optimal strategy, it's essentially has to be this textbook strategy that I just described. It can't be any other thing. And this fact also holds approximately. If you have an approximate winning, a strategy that wins approximately optimally, then these anti-commutation relations and these isometries all hold approximately. Okay, so this rigidity phenomenon is robust. So, you know, the CHSH game, one way of thinking about it, it's a way of testing for anti-commuting operators, and test for two-dimensional strategies. So what if you wanted to test for higher dimensional strategies? So one simple idea is you can play many instances of the CHSH game in parallel. So you have, you know, it's the same two boxes, but you just play n copies of it, and you check that they win all of the n instances. And it's not too hard to prove that, again, an optimal strategy, you know, you just sort of put all of them together, an optimal strategy will require a state space of dimension 2 to the n at least. But there's some undesirable aspects of this game. First of all, the maximum success probability goes down exponentially with the number of copies you take. And, you know, sort of more importantly for us, the complexity of this game scales linearly with n, right? If you're playing n copies of this game, you have to spend n times as much work to play this game. And so this is not that useful for us. So the thing that is useful for us is something called the quantum low degree test. And this comes from work of Natarajan and Vidic from a couple of years ago. And here they come up with a family of games, Q sub n, where for all n, the complexity of this game is polylogarithmic in n. The quantum value of each Q sub n is 1, okay? And this is a very nice feature. And also the entanglement lower bound, to win with probability at least 1 minus epsilon, you need at least, you know, essentially 2 to the n dimensional entanglement. There's some loss depending on epsilon, but importantly, the loss does not depend on n. It only depends on epsilon. And this C is some constant. Okay. So this quantum low degree test is really a workhorse for this compression theorem that I described earlier. Let me just say, you know, what's going on under the hood in this quantum low degree test. Maybe here's an algebraic reformulation of what it accomplishes. So any strategy that succeeds in Q sub n with probability 1 minus epsilon, so fix such a strategy. If you look at the algebra generated by the measurement operators of, say, box, you know, player A, you know, just take the algebra of that player. It must be an epsilon to the C approximate representation of this n-fold Weil-Heisenberg group. So this is the group right here. It's the tensor product of all these sigma x's and sigma z operators. There's also identities, and it's all possible strings. So essentially what this game certifies is that the measurement operators of the player gives rise to an approximate representation of this group, right? And this group, you know, non-trivial representations of it require dimension 2 to the n. The really non-trivial fact is that the approximation in this approximate representation does not depend on n. It only depends on how close you are to winning with probability 1. And also, you know, this is also a very helpful way of actually formulating the CHSH rigidity, that the simple, you know, game that I described before. Near optimal strategies for CHSH yield approximate representations of, you know, the Weil-Heisenberg group with just one coordinate.
So here's a question from Michael de la Salle. For which distance do you measure approximate representations?
Right. So in this case, you can take it to be, so it's the state dependent distance. So it's, you look at the distance between, like you take your operators and you apply it to the state that's used by the players. I mean, okay, so technically what happens is you apply some isometry to this, you know, you find some isometry, local isometry, and you apply it to the state. You know, you apply this isometry to what happens when you apply these operators on the state. This should be close to applying these Weil-Heisenberg operators on the maximally entangled state of dimension 2 to the n. And it's on these states that these operators satisfy all the, approximately the relations of this Weil-Heisenberg group.
Okay, yeah, thanks. So, yeah.
Sure. Okay. And so that's, one, maybe a more algebraic way of viewing what this test is doing. And how, where does it come from? What's going on underneath? So it's a quantum generalization of something called the low degree test from classical theoretical computer science, which in some sense, it's kind of like a non-local game with classical rigidity properties. And this low degree test, it's a non-local game, and it was crucial in proving this PCP theorem that is described many slides ago. Okay, so, and what do I mean by classical rigidity? It's, it's some class, so you assume that the players are using classical strategies, but when you play this game, it certifies some structure, some algebraic structure about what their deterministic strategy is doing. And it really says that their responses, in some sense, are consistent with low degree polynomials over a vector space over a finite field. Importantly, using only, very little complexity. So, these low degree polynomials over this vector space are very large objects, like they require, m to the d parameters to describe, but you can certify this structure using only polylog m complexity. So you can maybe start to see how this helps, feeds into the quantum version in the quantum low degree test. Okay, so that's all I'll say about that. And I think this brings me to my last slide. So here's some open questions. It'd be nice to have a simpler and shorter proof of the MIP star equals RE result, or, even further than that, a simpler, shorter proof of counter, the refutation of the embedding conjecture. There's still an open question of finding some explicit description of a counterexample to, that doesn't have this embedding property. Something that's, I think a lot of people are interested in is, trying to see if there exists a non-hyperlinear group. And it would be an interesting question to see whether our games could yield such a thing. So they would if our games could be formulated as what are called linear constraint system games. But it's not clear whether our games can be done, one can do that. And finally, there's a, this is more of a complexity theory question. One can consider what is the complexity of approximating the commuting operator value of a non-local game. So we showed that the tensor product value of a non-local game is as hard as solving the halting problem. The commuting operator value of the game is also undecidable, but can you reduce the, what's called the co-halting problem to that? And so that's an open question. And finally, I just wanted to make a quick advertisement. So I've set up an MIP star wiki page, and this is intended to be a resource for people who are interested in understanding our work. I know that there's been a bunch of reading groups at different places, and so this is sort of trying to be a central place to kind of provide, connect different people together and provide links to videos to different talks and put notes. And there's also a discussion board that that hopefully it could be useful to people to ask questions about this and have discussions. So with that, thank you very much for your attention, and happy to answer more questions.
Yeah, thank you. So anyway, so are there, thanks a lot for a wonderful talk. Are there, I'm kind of opening up for questions from the audience.
I'll jump in if nobody else is doing so. Lorenzo Sudun here. And that is a very blue sky question, which is that in quantum field theory, this result is sort of saying that you cannot approximate infinite dimensional things with finite dimensional objects. And there's a result of that flavor in quantum field theory that's been around since 1955. And that's Hogg's theorem, which talks about the non-existence of the interacting picture in quantum field theory, and essentially says that in an interactive quantum field theory, that you can't approximate the real states by just starting with the vacuum and then adding single particles a finite number of times with no limits on how many times you do that. So I don't see any direct technical connection. And after all, in Hogg's theorem, the Hilbert space you're adding is infinite dimensional each time. So a single step is not finite dimensional. So it's not literally the same thing as Kahn's theorem, Kahn's conjecture, but it sure has the same flavor. And I'm wondering if anybody has given any thought to whether there might be a connection there.
So, I'm not a mathematical physicist, so I won't be able to comment too intelligently about that, but maybe the other people can jump in. But the one thing I have heard from talking to people who are, they say that as far as we can tell, most quantum field theories, essentially all reasonable ones that you would consider, even though they're natively described using infinite dimensional Hilbert spaces, they all have this split property, which actually implies that they end up having a tensor product decomposition. So in some sense, this question of infinite versus finite for what people consider like physically relevant is kind of moot. So that's all I know about that.
Thanks.
So I have one question. When you get this poly-log time reduction, I can see how it scales down. I'm probably just missing something. Why do you not end up having some possibly infinitely many things that are constant bounded above size at the end?
Sorry, could you repeat the last part of your question?
So like at every time stage, it will shrink something roughly logarithmically. But at the very end, once the things are taking 5 time steps, why do you not have sort of infinitely many steps which take 5 time steps?
Oh, I think I understand. So you're sort of imagining that this compression procedure is sort of applied to itself many, many times. And the question is why don't you sort of bottom out at some like minimum constant or something?
Yeah.
Is that the question?
Yes.
Good. So I think maybe the right way of thinking about it is, I mean, even like, I think it's very tempting to think about applying this compression to itself many, many times, but it's actually never composed with itself. Like you never apply you don't do compressive G hat. That's not what this construction is doing. It's really, one way is you have these 2 infinite families. You have one infinite family of games, these G1 up to G infinity, and you're just applying compressed pointwise to each of them. And that's it. And you're sort of reasoning about each GI by first thinking about, well, what happened to Fi, Fn plus 1, and then, depending on how you set it up, the value of, Fn plus 1 should be related to Gn plus 1. So, so there's no, so at least in this picture, maybe it's easier to see why you don't, keep on applying this compression to the same thing over and over again.
Yeah, that helped clarify it. Thank you.
So I have a question, just a clarification. So in the compression algorithm, Okay, so you get this polylogarithmic complexity reduction. Is that used in the proof that you can have this kind of a recursive or self-referential step? So I guess I'm trying to understand where that's used.
The polylog.
Yeah, yeah.
Right.
So is that used in saying we are allowed, that G hat is allowed to like compress itself?
Yes, that's pretty much right. So,
Okay.
so actually, you know, we're on the slide that's relevant. You know, we've just written down some description of a game, and we want to say that it's we know what it's doing. So, so yeah, maybe I'll say that, you know, just that in a little more detail. So, you know, when we define this game G sub n, we're going to just force it to automatically time out after some polynomial number of steps, like regardless of whether it's finished doing what we want it to do.
Yeah.
Right. So let's say, you know, we just have a automatic abort switch at n to the 10 steps, for example. I mean, that's overkill, but it's just to you know, when we define it that way, then we know for sure each of the GNs actually does terminate in n to the 10 steps, regardless of what its behavior is. Okay, so then we want to say that actually all steps 1, 2, and 3 comfortably fit in n to the 10. And so when we do the counting, so step 1 takes n steps, step 2 takes a constant number of steps, step 3 takes polylog n, and so all of that finishes before the abort switch comes in. So that's where the polylog n comes in. And I guess you can see that it, you know, polylog n is leaves us a lot of room.
Okay, because if it wasn't polylog n, you know, if it was n or something, or poly n, then you wouldn't be able to compress G hat here is the...
Right.
Yeah.
Or it's something, you know, it would compress something, but we wouldn't know what to say about the output F.
Oh, okay.
Yeah.
Well, I'd say, you know, I want to thank you again for giving a great talk. And I mean, if there are no more questions, like I don't see any more, but just if there are no more questions, I just want to say thank you, and you know, I hope everybody stays safe, and everybody's doing. I hope everybody's doing well and staying safe. So thanks, and I'll probably see you on your wiki page.
Great. All right. Thank you very much. So, bye-bye.